it actually fits quite well that I speak now, so this is a seamless transition. So I will talk about the problem of spectral truncations of the torus. We already saw the example of the circle a little bit in the first talk. So let me remind you what we start with. We start with the canonical spectral triple associated to the D torus, which is given by this. So we have rough smooth functions on it. It acts on the L2 space of spinners, functions of the spinor bundle. And we have the Dirac operator. Then we have this usual distance formula. Last week we called it the Monge-Kantorovich distance, but you can associate even more names to it if you want. You just measure, so there's also some connection to optimal transport maybe. Yeah, we saw this also in the previous talks, and nothing new so far. And recall that the spectrum of the Dirac operator on the torus is given by this. So it's square roots of d sums of squares of integers. And the last piece of data we need to get our machinery started is the spectral projection. And so what we do is we project to the finite dimensional Hilbert subspace spanned by all the eigenfunctions associated to eigenvalues of absolute value at most lambda, which means that for each of these points, these lattice points in the ball of radius lambda, we get one eigenfunction. So the dimension of the space we project to is going to be, well, the number of lattice points in this ball of radius lambda. So maybe not too great, but that's just what we have to do to have an honest spectral projection. And with that, we form this truncated spectral triple that we saw this morning. So now we have an operator system which acts on this finite dimensional subspace, and we have a compressed Dirac operator. And the way you can think of elements of this operator system is this. So we saw this morning.
I get confused all the time.
So we saw this morning that in the one-dimensional case, we actually just get triplets matrices. And in our situation, you can think of this as triplets matrices as well somehow, but you have multi-indices. So yeah, this is just what elements of this operator system look like. We also have the distance formula on the state space of this operator system. And the question we're after is if the metric spaces that we get, if we take an increasing sequence of these projections, converge to the metric space that we have as the state space. And all of this is in Gromov-Hausdorff distance, so no Gromov-Hausdorff propinquity or quantum Gromov-Hausdorff distance so far, just Gromov-Hausdorff. Let's look at this problem a little bit closer. So this theorem was already pitched by Walter this morning. That's the device we're going to try to use. So what we need, or it's known in general that a sequence of operator system spectral triples converges in the Gromov-Hausdorff distance if you have this so-called C1 approximate order isomorphism, which consists of pairs of maps which go from the algebra down to the operator system, and another one which goes from the operator system back up to the algebra. These have to be unital, positive, contractive, and actually contractive both with respect to norm and with respect to Lipschitz norm. And they have to approximate the identity with respect to this Lipschitz norm. So I'm not going to talk about the proof of this, but this is going to be the device we're going to try to use. So you need candidates for these maps. This is just the picture to keep in the back of your mind. And this downward map here, that's already basically inherent in the problem. It's just the compression map. And it satisfies all these properties. It's a unital, positive, contractive. So that one's nice. And as a candidate for the upward map, Walter already mentioned that you can just kind of cook up a Fourier series out of your triplets matrix, because that's not going to be a positive map. But instead, what you do is this map, and I'm just kind of pulling this out of my hat, so bear with me. might make a remark about that, but it's a little bit shaky still. So what you do is you take this vector, which just consists of ones. So you have this, so if you take the cat bra of that, you just have a matrix full of ones. The alpha is the usual torus action on the operator system. And this map is kind of clearly positive, but you have to normalize to make it unital and contracted. And the number by which you have to normalize is this number, so the number of lattice points that you find in your ball of radius lambda. All right, so why do we take that map? Again, that's a bit mysterious, but what you see is that this map is actually the formal adjoint of this downward map. When you equip, when you take the L2 inner product here and the Hilbert-Schmidt inner product of matrices there. So maybe that means something, maybe not, and we can discuss that later. All right, so we have to estimate these compositions in Lipschitz norm. So let's compute them first. And what you see is that this composition, so you go down from the algebra to the operator system and back up. That composition is given by this. So you take a Fourier transform of your function, you multiply by this strange looking number, and you inverse Fourier transform. And this number is, this quotient is given by this. So you see that upstairs you have the intersection of, you take two balls of radius lambda, shift one out by n, and count the lattice points in the intersection. And downstairs, you have this number of lattice points in the ball that we already saw. That's just what you get if you compute this. So, okay. Maps like that have a name. They're called Fourier multipliers. If you take the Fourier transform, multiply by a symbol, and inverse Fourier transform, that's a Fourier multiplier. And well, the symbol I'm going to call M. And it's kind of straightforward. It's a small observation. This is completely supported, of course, because if you shift out the second ball by something larger than 2 lambda, you'll just find an empty intersection, so no lattice points to count. A couple of remarks. This Fourier multiplier can also be viewed as convolving with the convolution kernel, which is given by this. So here the symbol reappears. And in the one-dimensional case, we recover the Figee kernel. So in some sense, you can view this kernel here with this strange-looking quotient. You can view that as some kind of a higher dimensional Figee kernel. Let's compute the other composition. What you find is that you have these multi-index duplets matrices. And again, you have to multiply each entry of them by this number. So this is some kind of a Schur multiplication. And it's actually a Schur multiplier with the same symbol. So that's nice. We have these two compositions. One is a Fourier multiplier, one a Schur multiplier, both with the same symbol. You have to keep in mind that we have to take Lipschitz estimates of these compositions. So it's not enough just to estimate the norms of these operators that we get. So we need these Lipschitz estimates. And I'm just going to try to sneak a derivative of f in there. So now I'm just multiplying by 1. And what happened here is that this is, of course, the partial derivative of the Fourier transform of the derivative. This one I'm going to give a name. I'm going to call it W, which I'm sorry about that, looks quite similar to M, but and now what you see is that here again you have a Fourier multiplier, but now the symbol is W. You get a sum of D of these. I just need a little bit more space, so I'm just going to add another index. Nothing's happening so far. Now I have to remember how this function acts on the L2 space of sections of the spinor bundle. So on the spin part, the spinor part, nothing's happening. And this is this you can rewrite on this side as this anti-commutator of inward gamma matrices. And now you can pull this right-hand side apart a little bit, and you find this commutator with the function with the rough operator. So what we actually have to do is estimate this operator. And you can do a very similar computation for the second line and see that again you have some sum of Schur multipliers tensor with this. So just as a summary, this is what we're after. These are again these maps. Their domain is forms, so it's an operator system of forms. It's not the whole algebra, the whole operator system. But these are what we're after. And now, if you're a little bit familiar with Fourier and Schur multipliers, you might know that they are somehow related. So basically, Fourier and Schur multipliers actually are kind of the same thing. And we find something similar here, except that the ones that we're looking at are really defined in forms. And what we can show is, not trivial, but what you can show is that you can estimate the norm of this map SW by a FW. And this actually coincides with the norm of this, just with the norm because we're mapping into commutative C-star algebra. This classical theorem I mentioned before is the one by Bourget-Fentler from the 80s. You can find a very nice proof of that, for instance, in Pizier's book, but also in the book by Brown and Osawa, if you prefer that. And the way we proved our estimate here is actually we kind of adapted that a little bit. And I'm not going to go into full details of that because of time, but you basically have to find some kind of intertwining unitary of the two, and then all right. So what we're left with to show is that this map FW, that we can estimate that one. So let's look at it a bit closer. A reminder, this is what it is. And somehow this number m is kind of annoying. So we have to count lattice points to treat that number. And as always, when you have to count lattice points, you don't actually do it, but you measure volumes. So the idea is to replace this quotient of numbers of lattice points by a quotient of volumes and somehow sneak it in there. Now we can pull this apart and see that this operator we can estimate by this one and by this one. And this one might be a bit easier than this one, hopefully, because here we don't have to count lattice points. So I will talk about this one for a moment first, and then how we treated that one. All right, so this first one, no lattice point counting problem involved. What you find is, well, these are just some basic observations about this function theta, which is this quotient of volumes. This function is convexly supported. It's radially symmetric because when you measure volumes, really the shift parameter, when you measure the volume of this intersection of these balls, it really only matters how far you shift, but not what direction, which is not true for the lattice point counting problem. But for the volumes, that's true. It's continuous, evaluates to 1 and 2. And what you can show is, if you put all of this together, that we have good control of its Fourier transform. And this is a bit tedious to show because what you do is you kind of use an explicit expression for this volume of this intersection of these balls, which you can figure out. Use an explicit expression for this Fourier transform of a radially symmetric function. And if you put all of that together, you can explicitly compute the Fourier transform of this function theta and get that estimate. But it's just a bit tedious. But the way this proposition is set up is precisely to make this corollary work, which is proved by the Poisson summation formula. So this is precisely what you need for that. And what this tells you is that the convolution kernel, where as a symbol I take this function theta, this is a so-called good kernel. If you prefer, you can call it an ultimate identity in the Banach algebra L1 of the torus. So it just means it's absolutely integrable, integrates to 1, and all its mass is centered in that line. And now let's look at this operator again. This you can kind of sneak in this convolution kernel there by kind of doing the computation I showed you on the slide before. Do that backwards. So maybe that's just what we do. This is a very simple estimate. And then you see that this is what you get. So here you can pull out the Lipschitz constant of your function f. And you see that you have this integral, and you can show as a little exercise that this integral always converges to 0 whenever you have such a good kernel. And what this means is that we have good control of this first operator. So that one is fine, and that one converges to 0, and so now somehow we have to deal with this number of that. And the way I'm going to try to treat it is this. So I'm going to take a very rough estimate of this norm of this Fourier multiplier. As I said, the one we're after is not really a Fourier multiplier, but we can kind of adapt that to our setting. So the norm of a Fourier multiplier, you can show that it's estimated by the L2 norm of the symbol, which in general is very bad, right? I mean, the symbol is just a bounded sequence of ZD. Or this is an L infinity of ZD. So in general, this L2 norm might just be infinite. So it might be a rough estimate, but I'm going to try to get the most out of it. So what we're going to have to try to estimate is this one. And, well, this is just written out what it is. This doesn't look any easier, but here I just apply triangle equality. That's strategically kind of. And what you now find is these two quotients. And these have a name. They're called discrepancies by people who study this lattice point counting problem. And actually, the lattice point counting problem is precisely about estimating these discrepancies. Okay. So if you have good control of this, we should be in good shape. And note that we're dividing by this norm of n squared. So, which of course diverges if we're in higher dimensions. So if we let lambda grow. So we need really good control of these discrepancies to make this whole thing converge and actually turn to 0. And that's the challenge somehow. You can already start with very elementary considerations about this lattice point counting problem, because, well, the number of lattice points is actually the same thing as, well, you place a box of side length 1 around each of these lattice points, and you measure the volume of that. And then you can compare that to the volume of the ball. And if you do that, you get some rather rough estimate for these discrepancies, but they're enough to show that in the 2- and 3-dimensional case, this L2 norm I showed you on the previous slide converges to 0. And that's basically all I'm going to show you today. So what this means is that at least in that case, 2 and 3, dimension 2 and 3, this operator, the norm of this operator is bounded and converges to 0 as lambda is 10. All right. Now, if we put everything together, we get as a corollary this whole operator we were after. So I showed you this first part which did not involve any lattice point counting problem, and the second part which did estimated them individually, and in the case where in dimension 2 and 3, both of them converge to 0. So in that case, we're and then I use this lemma that we can estimate this operator S by this operator F, and we also get the same thing for that. And now, applying this criterion I showed you before, this means that these two maps, this map rho and this map sigma, this downward and upward map, that these constitute a C1 approximate order isomorphism. And this, by that criterion I showed you, means that spectral truncations, or the sequence of these state spaces, converges. Okay. So that's in dimension 2 and 3. All the same thing works, of course, in dimension 1 as well, and there you also have this estimate of these two operators, so that's nice. And a couple of remarks. For dimension 6 or higher, this does not work. So there's no hope that you have enough control of this lattice point counting problem. Actually, there are lower bounds for these discrepancies in the lattice point counting problem, which tell you this kind of estimate we used, this L2 estimate of the symbol, that's just not going to help you. Okay, that's a bit of a setback, but at least we got it for low dimensions. You might ask about dimension 4 and 5, what happens there? It's not so clear. You would have to look a bit closer at this lattice point counting problem. And I lied to you a little bit because when you count these lattice points in this lens, what actually happens is that this lens is not quite dilated when you let lambda grow, but it changes shape somehow. So it's not really the lattice point counting problem, but so you can't just rely on the results of that. You would have to do a little bit more. Okay, the reason why all of this does not work in higher dimensions is, as I said, that this estimate seems to be too rough, but that's kind of all we have at hand. And I thought I did not have enough time to explain this in detail, but I just put it in these remarks. But I want to mention at least that we computed the propagation number of these operator systems which are involved. This turns out to be 2 again, so independent of lambda, it's always 2. Maybe lambda has to be strictly greater than 1 or something. But it's always, in that case, it's always 2. And well, if you look at these 2-pits matrices, the way you compute the propagation numbers, you just multiply 2 2-pits matrices, and you see that somehow something that looks somewhat like a triplets matrix, but some of these diagonals have some zeros in there. And if you arrange that properly, you can kind of get all the matrix units back. And you might, in this higher dimensional setting, this is actually quite a bit more involved. It uses some more methods from convex geometry. So you basically find that you have to take these two intersections, take this intersection of these two balls, and you take 2 of them. You have to somehow be able to put them on top of each other or intersect them in a way that you can recover the matrix units. So that's kind of the game, but it's a little bit technical to spell all of that out. We're not so sure about the dual. So the dual of this operator system in the one-dimensional case, we had the triplet system. The dual we saw this morning is the Fégéry system. And the main device to make that work was this Fégéry's lemma, actually the operator value version of that. And that's a bit tricky in higher dimensions. So it's actually just not true that you can factor all positive polynomials in multiple variables by 2 polynomials which have kind of half the support. And I think it would be enough if you could do that for a dense subset of this positive cone of trigonometric polynomials. So if there are any experts on that in the audience, I'd be happy to discuss that later. But that's all I wanted to say so far. Thank you.
Use the disk to do the spectral truncation, but can you pick some other shape, like a blob or something? I mean, if you pick a square, then the counting problem is much easier, right? I mean,
this was done by a master's student artist, so he did it not for the disk, but for square. In that case, it basically comes down to taking tensor products of what you see for the circle. However, this is not really a spectral truncation, right? So if you really want to truncate to whatever you have, to all the eigenvalues that are less than your given parameter lambda. So somehow, because of that, you have to deal with this disk. And we had this idea, maybe you can take one box in one square in the disk and one square around it, and somehow approximate it with that. And one of the compositions seems to work quite well, but the other one that's kind of where it haunts you, so you can make it work.
Yeah, I was wondering about what's the C-star envelope for these operator systems?
That's just They're just bounded operators on this finite dimensional Hilbert space, where the dimension is the number of lattice points in the
matrices. Principle, yeah.
Yeah, of course.
Yeah.
And, as in the triplet system, the C-stratum was n by n triplets matrices, the C-stratum was just n by n matrices. And you basically have the same thing.
Further questions? Yes?
I have just a comment. I mean, I think when you have one of these C1 approximate identities, I cannot remember the name, then you also know that you have convergence in quantum of Hausdorff distance.
Thank you. Does that always work? Or?
When you have a C1 approximate identity, yes.
If I may, another small question. So I was wondering, I mean, you get templates, matrices, and so on, and of course, other ways of, if you have a compact Kelly manifold, there are other ways of producing this. For instance, Brilliant's interpolate quantization, where you represent your functions as multiplications on the set of homomorphic sections on some line bundle. You get similar things. I don't know, have you ever thought of, I mean, I think you can do this for tori because you can get hold of the homomorphic sections, but did you think about any relation to that kind of truncation? No. Okay.
For spheres, this is what reflow does, essentially.
Yeah, sure.
It's algebra.
Yeah. But in this case, maybe if it's completely different, or
yeah. Well, the structure is similar, so
sure. Yeah.
Further questions? Okay, then let's thank Malte again.